Hello and welcome to today's seminar, Turn Rocks into Money, How XRF Enables Profitable Mineral and Metal Mining. My name is Frank Portala and I'd like to guide you through today's seminar. First of all, I'd like to give you a brief outline about the seminar. So after an introduction to XRF, we are showing you XRF applications from exploration to concentrates. Then we will switch to the lab where we introduce you to best practices of sample preparation. Back in the studio, we are covering metal mining applications from base to precious to rare metal earth elements. And then we are heading back into the lab again and show you turnkey solutions for WDXRF. I'll then conclude with a short summary, and then we will head over to the Q&A session with our experts. Today's speakers are Kai Behrens and Adrian Fiege from the product management team in Karlsruhe, and then Renata Janic, which is our application specialist in the lab. And with this, I'd already like to hand over to Kai and Adrian. Thank you very much.
Good morning, good afternoon, and good evening. My name is Kai Behrens, and with me is
Adrian Fiege.
Yeah. Many thanks for joining our webinar. Today we want to talk about the topic Turn Rocks into Money and how XRF can help you to have profitable minerals and mining operations. And we will look into the way of XRF applications from exploration to concentrations. So first of all, we need to understand when we talk about minerals and mining operations, we need to understand that element concentrations are providing the very vital information, the value of our material. So first we look into exploration and mine planning, and of course the value of the resource is determined by the total amount of the valuable material like iron, copper or gold. And then, of course, there are hazardous elements present or elements which are having influence on the mineral beneficiation process, and they are decreasing the commercial value. When we have understood this, then actually we can go into the mine operation, and of course the mine output is typically based on the high grade, low grade and waste material and the ratio between them. So we need to separate them, and of course we need to do a pretty tight process control in order to drive this very costly process of milling and separating into the most profitable way. And of course then when we have our final product grades, we talk about shipping. And first of all we need to understand what is really inside our product. And then, of course, actually have an alignment between the seller, the buyer, and the contractors in between, to ease payment. Yeah. And last but not least, of course, then we are at the metal production side where the element concentration is important to really fine-tune the final product, the metal alloy.
Yeah, so overall, there's a lot of reason for doing elemental analysis along the value chain in mining. Because it really helps you to define the value, the money that is within your rocks.
So first of all, jump into the topic, what is the optimal tool for this task? And of course, we are pretty sure it's XRF, or Adrian?
Correct. And so to get everybody up to speed, we start with a little bit of an introduction. So what XRF does, we have an X-ray tube, an X-ray source, that excites our sample, what means that we are ejecting some inner shell electrons from the atoms, and then outer shell electrons fall into the vacancy. This emits some characteristic X-rays, which are characteristic for that transition, and which can then be detected. And we can detect either count the electrons and separate them first by their wavelength, or we simply count them in a silicon drift detector and also at the same time determine the energy. So overall, this technology really makes us quite independent from the material, from the next neighbor bonding, and so we can measure a wide range of elemental concentration and elements in one go.
Yeah, the interesting thing, since you said this, it's independent of the chemical bonding, actually we doesn't care about if this is a solid, a liquid. So we are in the position to analyze the rock directly. We are in the position to analyze a powder or even a leaching fluid, a slurry, and would get pretty good results.
Yeah. So we can categorize XRF analysis into three main categories. One is a qualitative assessment. There we basically get an idea of what's inside, what kind of elements are inside my material, my sample. Then we have quantitative analysis. That's what we typically do in mining, mineral beneficiation. So here we want to really know the concentration as accurate as possible. So how much of each element is inside. And then there's also something in between, semi-quantitative approaches or also standardless approaches based on fundamental parameters, which give us quantitative results, but maybe not as accurate, but are nice for screening, for fast screening. So one of the big advantages with XRF, Kai said it already, is that we can use most of the samples as they are, so liquids, solids, and we need really relatively minimal sample preparation to present them to the instrument. We'll go over some of the details throughout today's talk. The small amount of sample preparation also results in a very short time to result from actually getting the sample to getting the result. So the measurement time is one aspect, of course, but it's also important how long does it take actually for me to present the sample to the instrument. And this is where XRF is really strong. Overall, we have a very long stability of the system, which means once we have calibrated the system, it can be used. The calibration is valid for a very long time. It's just monitored, sometimes a bit adjusted, but basically you can work from the morning to the evening, next day, next week, next month with the same calibration. And we already mentioned it, we can cover a very wide range of concentrations and elements. So in one method, with one sample, we can be able to measure majors, minors, and traces. Depends again a bit on the presentation of the sample, so on the preparation. But this is also possible with XRF.
So actually, to emphasize this again for the mineral business, it means we have a fast base for decision making. Data are available in pretty short time. And actually, we can cover with this one tool the entire element range and the entire concentration range. So no matter if this is a waste material and we have low concentration of copper,
exactly.
or if this is a high-grade ore or concentrate with higher concentration.
Exactly.
That sounds pretty cool, and yeah, have a look.
Yeah, that's the beauty of XRF. And there are a few other things to keep in mind compared to other technologies. So other technologies are mainly ICP, so spectroscopic methods, and AAS. And here, one of the main disadvantages is that we have to first dissolve the sample. So we actually have to change the matrix, remove the matrix if you want. So we have to also dilute it between major elements and trace elements, different dilution ranges, so not everything at once. It is not as simple as to use, so XRF is really, once it's calibrated, and calibration is not that difficult either, but once it's calibrated, it's really pushing the button and off you go. We also don't have with XRF such expensive consumables or hazardous consumables, so you really don't need a lab technician to operate this system. You don't need a fume hood, for example. So there's a lot of investment which you can spare. And so overall, especially also with the lack of need for noble gases like argon, you have a really much lower cost per analysis. And this really reduces your cost of ownership. On the other side, you can also save money on the, let's say, expensive stuff. Yeah.
So actually the nice thing to understand for minerals mining operations, especially when we are in the outback or somewhere on remote areas, the lab standardization is pretty easy and straightforward. So we calibrate the instrument once and then it's just running a few drift correction samples. So we can maintain an accurate, precise method over a long period of time and also align different sites within a company and having comparable analytical values, which helps to transfer the knowledge pretty easily.
Exactly, yeah. So broadly speaking, there are two main technologies. There's a bit more to that, but just roughly speaking, we have an energy dispersive system here on the far right-hand side. We have a tube, then the sample, few optimizing components like beam filter and maybe masks, and then we have a silicon drift detector that detects both the incoming photons and their energy. And then here to my right, we have the wavelength-dispersive system. There we are going in with much more power, 400 watt to 4 kilowatt. We have more components on the way, like collimators and especially the analyzer crystals in the goniometer. And this is the heart of the instrument, which also separates it significantly from the energy dispersive system. Here we are separating the fluorescence photons from the sample based on the wavelength. And this allows us to get a much higher sensitivity at the end of the day. We will go through some examples in the talk. So how do we present the sample? There are different ways to present a sample. Like Kai also expressed, you can sometimes even use the sample as is. In mining, however, typically you need to homogenize a bit. You have a rock. This rock is never really homogeneous. Some are more, some are less, but you typically need to crush it, grind it to homogenize the sample. This is what you need to do essentially for all samples. You need to make sure that your sampling is also representative for the information you want to get. And then in mining, you have basically two major types of preparation. This is here so-called fused bead on the lower side, and then up there it's the pressed powder pellet. This is what is mostly used. We will describe a bit what are the pros and cons later on, but mainly what you can imagine, of course, with the fused bead, you use a flux, so you dilute the sample a bit more. But on the other hand, you get a very homogeneous sample with a very smooth surface. Pressed pellet is something you can much easier put into an instrument. This is something that is really often used in mining, but you need to take a bit more care about grain size and smooth surface, for example.
Yeah. Means actually, and this is easy to understand from this picture, means there is a kind of grain distribution which limits almost a little bit the precision and accuracy which we can achieve. And then we have the fused bead, which looks almost perfect, so with a homogeneous distribution. So I would say the first one really has a mineral operation, and the second one, the fused bead, is come into play when we talk about the shipment of our product, the grade control.
Yeah. So now let's jump a bit more into the value chain. So start with exploration at the very beginning. Maybe Kai, you can tell us a bit more there.
Yeah, means when we look into a countryside and we think there is a potential resource, the geological survey is doing the mapping, the distribution of the resources in the country. So we want to classify the mineral resources. We want to understand how the valuable elements are distributed in this zone, and if they are bound to specific minerals. And this makes mapping based on drill cores, blast hole analysis very important to decide what is happening later. Is there value enough to be mined? The second thing, what are the costs of the mineral beneficiation? And this also leads to the decision path for rock sorting, the separation, if this should be leaching or flotation. And actually, of course, we also need to understand that when we are running bulk analysis, we are looking at the concentration per ton, but the distribution is not always homogeneous. So therefore, we have a huge amount of samples which we need to cover. And yes, this can become quite costly. Right?
Yeah. So I can imagine that, especially in exploration, we are dealing from side to side. These are natural deposits, so they are all different. So we're dealing with various types of materials and various types of interfering minerals, for example. So I guess we need a very versatile solution there.
Yeah, so first of all, we want to have a high sensitivity. We don't need the highest accuracy. So therefore, we look to some preparation method with very low dilution, because this is best for traces. And we need high count rate, therefore. And sometimes we also have volatile elements. We can imagine if we are doing a fused bead under heating, we might lose sulfur or chlorine. and we are looking for a huge amount of samples, so we need low cost. So that's basically in the pros to go for pressed pellet. The second one is the cons, of course. The reference material must match the matrix and mineralogy, and this can be quite a challenge. So there are some caveats in terms of accuracy maybe, and the grain size must match to the standards, which sometimes is a little bit difficult, because when we look at limestone, it's pretty soft material and compared to granites, which are pretty hard. So therefore, there are some particle size effects. Nevertheless, we want to understand the distribution. We are not looking at the very highest accuracy.
So if I get you right, it also means that if you want to measure fast and simple, but also get to the highest amount of concentration limits, like trace limits, then really pressed pellet is the way to go. But what about the method itself?
Means actually, we need to understand when we look at geological samples, and here is a scan of a geological sample, we see a huge variety of elements in. Some are very high intensity, the majors like calcium or iron, and some are pretty low. And so we analyze large set of samples, we have a wide range of elements and concentrations, and we need a quick sample preparation. That's the exploration application. The challenges are we have a huge amount of spectral line overlays, so we need a good resolving instrument, and so therefore maybe there are some special crystals involved. The second thing is trace analyzer require high power because we need high sensitivity. So on the one hand, we are looking at high excitation power. It's the instruments up to 4 kilowatt. And then actually we can also optimize with specific crystals. And we need to scan a lot of positions because we also need to access the background, the spectral background, in order to subtract from the sensitivity for the traces. So that sounds a little bit complicated, but I guess we have a great news for you. As I told you, we have an instrument, and the nice thing in XRF is we can basically standardize an application and put calibration in place once when we set up the instrument and then run it over the lifetime of the instrument. And this we also can do in the factory. So we have come up with a package called GeoQuant traces. And that's actually a method which are covering more than 60 elements, more than 50 trace elements and major elements. And actually this is a perfect package for the mineral exploration work. So in geological research, when we look for rare earth elements, precious metals, when we do environmental monitoring, or when we look for resources, that's a pretty cool thing. The second is we can also adapt this method. So when we don't need the rare earth elements, or we know there are no precious metals inside, we can skip those elements and increase the throughput of machines. And if we have the idea in optimizing the sample preparation, this can be adapted. So it's like a Swiss knife, which can target actually our exploration application.
Yeah, this is really nice, going back to the point that, you know, in an exploration, your deposit to the next deposit is different. And not each time you have the time and money maybe to do method development, to, you know, really fine-tune your instrument for the new type of rocks you're looking at. And there, this package is really useful.
Yeah. So actually, samples are prepared as pressed powders. This reduces the preparation time. It gives higher intensity. On the other hand, also the matrix elements, which might not be so interesting, but they are analyzed and taken into account to have a matrix correction giving a higher accuracy. And of course, we have set up the measurement method in the way that the typical LOD is about 1 ppm. This can be improved by prolonging the measurement time per element if I look towards a specific element. And yeah, sometimes we even can achieve sub ppm in a pretty good way. Yeah, so that's an example of a really nice method which can be factory installed and then transferred and maintained over the lifetime of the instrument.
Excellent. Thank you, Kai.
So we talked about pressed powder. Nevertheless, the fusion is in a lot of applications the preferred method. So what does it mean? We take the sample and we flux it with borate flux at high temperature and put it in a mold and let it cool down. So actually we transform the powder into a glass sample, a homogeneous glass sample. So, and all different compounds of an element are transferred into oxide, stable oxide. So, and therefore we can transfer almost every mineral into the stable glass sample. And this gives better homogeneity, and this enhances basically accuracy. And also the dilution helps to really analyze very accurately also the major elements when we think about iron ore resources. And the dilution also helps with a match of the matrix and the mineralogical composition to the certified reference material. So those are the nice thing of fused beads.
Yeah. So maybe to add to that very briefly, there's of course always a bit of a sweet spot for the two types of preparation, may it be pressed pellet or fused bead, and that's something we can always help you with. So for instance, you can imagine when you're really looking to the traces, then the dilution rate that you're dealing with fused beads might be a problem. Here we have some examples for different fused recipes, and Kai will go into that maybe in a few seconds. And but then you can also imagine that of course there are some ores which are more like copper ores, for example. They have relatively high concentration of the element of interest, copper, but you want to know that maybe relatively precise, and you're dealing with a very complex and diverse mineralogy which causes effects. So then fused bead is definitely the way to go.
Yeah. So here you find a table from our friends XRF Scientific. They have come up with recipes. And what you see is that we can have lithium tetraborate and lithium metaborate in a mixture. So actually we are fine-tuning the melt temperature. And you can see that there are different materials. So like cement is very easy to fuse. So it can be a very high sample amount within a lower amount of flux. And then we don't need an oxidant. When we look at iron ore, there we prefer to have a 50-50 ratio. And also we will add some oxidant in terms to protect the platinum ware and also help with the dilution of the sample. Pretty tricky is, in another word, the sulfides. There we need more oxidant because of the sulfur. So actually there is a little bit complexity in these recipes. The nice thing is they are already available and for the machines. So actually it's a pretty straightforward way just following this guideline.
Yeah. And with those words, we will actually now switch to the lab for the first time over to Renata, and she will tell you a little bit more about the sample preparation, give you some tips and tricks, and we'll see you later here back in the studio.
Hello, also a welcome from my side. My name is Renata Janic. I'm working here as application scientist for XRF, and right now we are in our facility in Karlsruhe in the application preparation lab. Today I would like to show you some more detailed and give you some information about sample preparation in the mining area. I already prepared some material to give you some information. Typically in the mining area, let's say most common prepared samples are fused beads and pressed pellets. Let's start with pressed pellets. Here there is a pressed pellet from an iron ore sample, as you can see it here. So when the samples are coarse, of course you have to grind the samples first. In our lab we use a tungsten carbide vessel, which is of course a small one here, where you can fill maybe about 20 or 30 grams of sample, and you can grind them to get some fine powder, which can be used to prepare the pressed pellets. The vessels are available in different materials. So I think the most common materials which are used in this area are steel vessels and tungsten carbide vessels. The big advantage of a tungsten carbide vessel, it's a very hard material, so you can grind more everything, all material. What you have to think about is, of course, that for each vessel material, you also have some contaminations. So for a steel vessel, you will, of course, have some steel or maybe some chromine as traces, which is contaminating the material. And for tungsten carbide, of course, you will see always some traces of tungsten and, of course, also some cobalt. After the material is grinded, you can mix the sample. Here in our lab, if I prepare a press pellet manually, typically we use some wax, which is diluted 1 to 10 into the sample and can be then pressed very easily. If an automation unit is used, then typically you will have this kind of grinding aid tablets, which are just added to the material, maybe 2 or 3, depends on the recipe, and then the sample is grinded with the binding tablets and a press pellet is prepared. Press pellets are very easy to prepare, they're not as time consuming as fused beads, and also the costs are lower than for a fused bead preparation. But the big advantage is the mineralogy. So especially in the, or let's say from the beginning of the process, you will have different mineralogy. If you have samples from different sites, this will mainly affect your analysis. So in this case, like for example, also for big labs, or if you have a central lab, then typically fused beads are prepared. Here, for example, we can see a very nice prepared fused bead, which is a copper ore. Fused beads preparation can be sometimes not as easy as preparing a press pellet. So it always depends on, is it a full, let's say, oxidized sample, then it's very easy. So you can use maybe 1 gram or 0.8 gram of sample. You can mix it with 8 to 10 gram of flux, which is mainly a mixture of lithium tetraborate and metaborate. It can be 50-50 or 64-35. Then you can just mix it very easily, 1 to 10, into the flux, and you can prepare the fused beads. So in this case, you will use these platinum crucibles. So typically I would touch them only with gloves. So here today it's an old crucible. So you just mix the sample with the flux. In this case, I always try, I use a little spatula and to mix the sample. I always try to avoid to touch the platinum crucible inside with a spatula. So you can also use, for example, a glass one or a little spatula. After the sample is mixed, you can just put it into your fusion device and then the fusion process starts. On the other side, we have also to talk about samples which maybe contain some metals, if iron is not oxidized or some other ore material. So then it's very difficult to prepare fusion, and so you can also destroy the platinum crucible. So in this case, you always have to make sure that the sample is oxidized. So there are different ways how to do this. So here in our lab, I do have enough time. So typically what I do first, I ignite the sample first. In a mining production unit where there's always some lack of time due to the high process number of process samples, then typically the sample is not ignited. In this case, you would run some oxidation steps while the fusion process is running. So this means you will have different temperature steps or temperature ramps where the sample is heated up. So the temperature which is used also depends a little bit of the material which is used. And you will have some additives. So I think in the most cases you would use sodium nitrate, which is used to oxidize the sample. Sodium nitrate can be used very easily. It's not hygroscopic and it's also not part, so sodium is not part of the iron ore norm, so therefore it can be easily used to prepare the fused bead. To clean the crucibles, sometimes this is also can be a hard job. So in our lab here, we use ultrasonic bath, and if the crucible is quite dirty, we also add some citric acid just to make sure that the sample or the crucible is cleaned. What can also be after a long time of use, if this molds, so with time there will get a lot of scratches, and this can maybe also influence the surface, the measurement surface of the fuse bead. So what you can do, you can always use the material, the old material, send it to the producer. They will produce new platinum crucibles or molds. But in our lab, we also have a good positive experience with just some little tool which is used with some paste to get the surface nice again. So this is also one alternative way to get a nice mold again. You should always keep the molds clean. You should make sure that they are not scratched, that they're handled in a nice way, that they are not stored somewhere in the crucible. So what we do have in our lab, which is very nice, is this, let's say, tool which is used to transport and to store the crucibles and the molds in our lab. So this is quite nice. And so I think these are maybe the, let's say, the most important things about sample preparation in the mining. To show you a little bit how the sample is casted in a fusion device. So here I already started one measurement, and I will just go to the fusion machine and will show you how this works. So we're just in time. Here you can see this is an electrical device with a muffle furnace. The sample was heated and also the mold was heated. And now you can see how the sample is casted into the mold. After the sample is poured, the system will cool the mold so the sample can be released manually out of the system. That's it. The fusion process is now finished. Okay, so that's all from me at the moment. So for the first session, see you later in the second part. Thanks. Let's go back to the studio.
Yeah, thank you, Renata, for showing us some details about sample preparation. Really interesting. So now welcome back to the studio. In the second part of today's webinar, we want to talk a bit more about key applications. So from base metals, precious metals to rare metals. And let's start with one first example, and that is nickel mining. And nickel has become a very important, it always was, but it's becoming even more important now with electric vehicles. The demand is rising, and especially the so-called nickel laterite is becoming the dominant source for nickel for our society. And here the energy dispersive systems can really excel the tasks that we are looking here into. So we of course want for these nickel laterites, which are so-called low-grade ores. So we talk about a few percent of nickel in the sample. So we want, of course, to have accurate measurements of nickel, but then also we want to measure the waste rock. Here we're looking into calcium, magnesium, iron, manganese, for example. We want to evaluate some traces, and we want to do all this in a short time and by loading sample after sample quickly. So this is why pressed pellet is basically the way to go for this kind of analysis. And it's also very helpful if I have a device where I can load samples at any time, so an XY auto changer. So the S2 Puma Series 2, which is our energy dispersive system here, really excels. You can measure a pressed pellet from a nickel laterite mine or deposit in a few minutes, and this is really possible with our high-sense detector technology and our 50-watt tube. We can really get a high precision and accuracy within just 2 minutes from or less from time to result. Another point that is really important in mining is how do we protect our systems from spillages, from contamination. So you might imagine, so in a mine, in a remote situation, it's a very really dusty environment. So we can have pellets that may break, they may contaminate the system, these powders may get into the system. How do we prevent the system getting damaged by that? For this, with all our spectrometers, we have a very unique way to protect the spectrometers and especially the vital components. This is the tube and the detector, especially in the wavelength-dispersive part. It's the entire goniometer that you want to protect. And this is what we call sample care. Here on my right-hand side, it's simply illustrated for the S2 Puma beam path, where we have the filter wheel, which protects the tube on the far right here. That's the filter wheel here. Then we have a reservoir. So in case a sample breaks, it goes into that reservoir and you can clean it. So you don't need a service technician to come. And we have a detector cap that protects the detector from these spillages. And also with the XY auto changer and our smart USP, which can be hooked up to the system, the samples will be retrieved from the sample changer in the case of power outage. Another point that can be important for remote locations. So another topic that we want to discuss here is rare earth elements. So rare earth elements are playing a big role. They are not as rare as the naming, but they are still quite rare across the globe, especially in terms of exploitable resources. So as you can see here on my right-hand side, there are only a few countries really contributing to the overall mining per year. And you can see also that there's a huge uptick of the production, of the annual production of rare earth elements. And why is this? Well, because it's used in many technologies that are, well, becoming more and more important, like looking into the energy transition. So for example, in magnets, you need them in the wind turbines, you need them in electric vehicles, you need them in catalysts, you need them in your cell phones, for example. Yeah. So how do we analyze such material? Well, first of all, these are relatively low concentrations, but not super low. Then you are dealing with a wide number of elements within these rare earths. You can also separate them by light rare earths and heavier earths. That's a bit based on their natural abundance in the Earth system, basically in the different Earth environments. But because of this relationship that they are all behaving quite similar, you can do a little trick here. And this allows us to get, especially for exploration part of work, to get a good assessment of the total rare earth concentration because of their relative abundance being related based on the element which has the highest concentration. So this is a workaround that we can do here. So we can, for example, say that yttrium is proportional for a given type of material, given region, given deposit to the concentration of total heavy rare earth elements. And this little workaround allows us to actually determine the, in this case, the heavy rare earth elements with a simple energy dispersive system like the S2 Puma quite accurately. So here we see just the measurement results for yttrium in the relatively lower ppm range, so 17 ppm, and we see really a high precision. So this makes an energy dispersive tool for some simple rare earth assessment when you go into the field, or also when you want to when you have your deposit and want to get a quick idea about is this area that we are drilling right now still in the high range or in the low range, you can use an energy dispersive system.
So this has been quite a winning strategy in a lot of cases where you are using a tracer element to direct you into the right direction, and you don't analyze particularly each element, but use a tracer in order to get an idea. And this helps especially in exploration work, right?
Yeah, exactly. So now we have basically had two examples where energy dispersive systems can be the optimal solution for mining. But Kai, I guess there are a couple good examples for wavelength dispersive.
Yeah, I mean, so, the big difference here is actually the wavelength dispersive provides a better spectral resolution. And we can see this example here where we see the iron peak. The yellow curve is the ED spectrum. The black is the wavelength dispersive spectrum. And this is a very critical difference between the two technologies. The one is basically analyzing simultaneously the range of elements. The other one can be optimized element by element and therefore is giving us the right answer. Here we see that iron and manganese is covered under the one peak in ED, but separated in wavelength dispersive. And this gives us some indication that those applications might be better to be done with wavelength dispersive. Others are okay with energy dispersive.
Yeah. And this is what we see by our customers. So our customers, when it comes to high precision, they are using wavelength dispersive, mostly large wavelength dispersive systems. When it comes to when it comes to some maybe backup or also some easier tasks, some screening, some promoting analytical parts, an energy dispersive system like the example I just brought can be sufficient. Sometimes you're in between the two, and this is where benchtop wavelength dispersive often comes into play. So we have the S6 Jaguar here, which is a quite new instrument with 400 watt tube and with a generator that allows us to use the system even at full power for light elements, so at low kV. It's equipped with a 4-position beam filter. We have a 4-position sample mask changer, and we have a vacuum seal that really protects our system and also reduces the amount of gas that we need, so really reduces the operational costs. So together with the high-sense technology, so especially the high-sense XE detector, we can really excel many tasks that can be done on a full-blown wavelength dispersive system. We might just need here and there a bit more time to count. And this makes it often the first choice, or at least a very good backup system for those who need the resolution of a wavelength dispersive system. And one example we want to bring here for the performance of the S6 Jaguar is the analysis of coke, coal, carbon materials. Again, not just a topic for energy production, but also for energy storage, as we need the graphite, for example, in our batteries. Depending on the application later on, we are looking into various elements. So we don't care so much about the carbon. What we care about is the impurities, because the impurities later define essentially the value of the product we have here. So for instance, looking into chlorine, which can have corrosive effects based on the later use, or looking into sulfur concentration because of its impact to the environment if it's used for energy production. So here we can just briefly scan into what the S6 Jaguar can do. On Kai's side of the screen, you see a correlation curve for nickel, which is an important trace element also to cover where we get with a benchtop wavelength dispersive system down to a lower limit of detection of 0.4 ppm. So this is really extraordinary. And if you digest these tables here, you can essentially see that we are matching the certified value quite closely. For example, here in nickel, we are very close to the concentration of the certified value of 128 ppm to 124 ppm, and with a high precision. This is done with the S6 Jaguar. But of course, there are some limits, and especially when it comes to throughput, counting and also lowest traces, counting statistics matter. And maybe Kai, you can elaborate a little bit about the matter of counting statistics.
Yeah, I mean, I don't want to bore you with mathematics, but actually there is a principle. It means there's a counting statistical error, and this actually determines how precise we can be. And actually taken into account that we are having for one element 100 counts, total count rate, actually we will see that our counting statistical error is 30%. And in the moment we are adding more counts, we are bringing this down. So assuming that major elements we count with 10 million counts in total, we will go down to 0.1%. And this shows exactly why we are now talking about 50 watt for ED, 400 watt for the benchtop WD, and now we are moving forward to up to 4 kilowatt with our SA Tiger, which means that we are putting a higher power, excitation power into the sample. And of course, when we have a detector which can deal with this high count rate, then actually we are achieving very high precision. So we call this high sense counting electronics. And the trick is that we have a multi-channel analyzer, which on the one hand sums up all the counts very fast. And this helps us to achieve count rates like up to 2 million for the flow counter and scintillation counter without any correction. And when we apply the Dynamatch technology, we can go up to 30 million counts per second. The interesting thing hereby is that those count rates are not for the entire spectrum, but we are counting at one element at a time. And so therefore, when we are able to analyze iron with a count rate of 2 million counts per second, we are pretty fast and getting very precise results. So, and this is especially important when we go to process control or to grade control. One other detector in our high-sense detector family is when we think about the mineral applications, we also know that there are remote places. And up to now, wavelength-dispersive requires flow counter gas. And the problem sometimes is that this P10 gas, argon methane, when we forget to order just in time, we are out. We cannot analyze the light elements. And here we come up with a new detector. It's called high-sense GF, gas-free, and this covers the range of the light elements up to manganese. And the nice thing, it's a sealed flow counter with a high transmission window. It doesn't require any maintenance, and so therefore it's ideal for remote places. And this has been just introduced. It's manufactured in our facility in Germany, and this is now available for SA Tiger. It's a great deal whenever we are thinking about remote places. So we talked about the GeoQuant traces on the one hand. Nevertheless, there are more packages. Means we also have the GeoQuant Basic, which are just covering the major and minor elements in geological samples, or the GeoQuant Advanced, which on the other hand also have some of the, let's say, not so common minors. And then we are ending up with iron ore, GeoQuant iron ore, which is a dedicated package for the iron ore industry. And here I would like to have a closer look to this business. Means iron ore, when we talk about iron ore, we talk about huge amount of tons. And of course, the ore producer itself is looking for total iron ore grade, beneficiation, the milling, washing, the magnetic separation, the sinter pellets, and of course the shipping. And in all those cases, XRF is involved, especially the fast grade control, where we have an international norm called ISO 9516. Actually, this tells us more how it's accurately done. And the goal is maybe not to be perfectly right, but the goal is to have comparable data across the globe. Because yeah, you can imagine that it's tough negotiation when you have a deviation between Australia, China, or Australia and Germany, about 0.1% deviation, right? And then, of course, we find XRF and XRD also in the metal production itself. So the GeoQuant iron ore package actually contains 16 certified reference materials, evaluation samples where we can check the quality check sample and manuals. And this enables on the one hand the grade control following ISO 9516, but also the process control. So there's also a pressed powder method available. And it covers the 21 elements which are described in the norm, including the sodium. And the nice trick here is we are working with pressed powder pellets for process control or few speeds in grade control. And we have two matrix correction models. The one is the variable alpha model, which enables the method to handle a huge variety, even low-grade iron ores. And we have the loss eliminated alpha method. This is following the ISO 9516. So actually here, this comes straight out of the box, can be installed in every lab, taking the lab sample preparation into account, and then we are ready to go.
So it's really an extraordinary dedicated solution for the iron ore mining here, Kai.
Yeah. And actually, those are the data we achieve looking at the accuracy test with NIST 690. And we can see when we are diving into the table, looking at the min, max value, the mean value, and compare this to the certified value, we see that the standard deviation is pretty small, even below, in a lot of cases, below 0.0 or 0.1%. And when we think about the precision and accuracy level, 0.1%, when we have a bulk carrier with about 100,000 tons load carrying with high-grade ores, we talk about 80,000 tons of iron with a value of something like $8 million. 0.1% less precision means $8,000. And this easily sums up if we are doing a mistake, which is even higher. So,
yeah. And with that, we are back to the motto of the day. So turn rocks into money. You need the precision to really do this task.
Yeah. Nevertheless, when we talk about a service lab, a geological service lab in the harbor, when we talk about central labs, we also have the feeling, hey, we have huge amount of samples. And there we come to a different class of instrument. The Tiger actually analyzes sequentially element by element with optimal settings and changing. It has a crystal changer, a collimator changer. It switches from low kV to high kV. For some applications like the service labs or central labs, we have a so-called simultaneous wavelength-dispersive unit. This is configured to cover the element range for a particular application. And each element has a dedicated channel. And equipped with an auto changer of 90 samples, actually we have typical measurement times of less than 1 minute per sample, which means that we can process more than 60 samples per hour, which is kind of Formula 1 speed.
Mm-hmm. But for that, I guess you need a really extraordinary precision and stability, don't you?
Exactly. Taking into account that there is no moving part, we just move the sample in, we have fixed channels. We see that the iron repeatability is great, even below 0.1%. And also looking at an important penalty element like phosphorus or silicon, we are in a level of 300 ppm. We are in a relative standard deviation of about 0.2%, which means it's world record, right?
Yeah. So maybe as a last example, let's look into sulfide ores there. And we've heard a bit about the present preparation here. What's the ideal method now?
Yeah, I mean, copper sulfide ore, on the one hand, we have high sulfur, and this sometimes is a little bit challenging, but it's doable when we look into the fusion device. The most important thing is we need to protect the platinum dishes. Otherwise, we will destroy during the platinum or during the preparation, and the ore get into contact with the platinum, we will destroy the platinum, which can be quite costly. The problem with the press pellet calibration is that it will suffer because the sulfur, if this is sulfide or sulfate, this has a huge influence on the mineralogy, but also on the stoichiometry. So for accurate analysis, we really need to have those few speed approach. The concentrate itself show pretty low variation, so therefore we can go ahead with press pellets because those are also processed materials with some kind of homogeneous grain size.
Mm-hmm. Let's maybe look a little bit further into a recipe for fuse speeds. We have now heard a few words about that. It's quite complex, for this material.
Yeah, so again, our friends from Australia, XRF Scientific, they have come up with a recipe. So actually, you take a little bit lower amount of sample. You take flux ratio between lithium tetraborate and metal borates at 12 to 22. You take oxidizer, sodium nitrate, which on the one hand also means that we can't determine sodium, but that's not an issue. This oxidizer helps to really quickly oxidize the material that we don't harm the platinum ware, and easily also go into a state where we can form stable glass beads. And then we have a release agent which releases ammonium. It's a tablet, and this is put into the sample close before casting. So, and you see the temperature program. The nice thing today is that those programs are run automatically, and it's a preparation time of about 20 minutes, but there are multiple position fluxes available, and they go automatically from stage to stage, also have the cooling integrated, so therefore it's highly automated. Yeah.
Yeah, switching back to concentrates, if we do this with pressed pellet, what type of device do we use there?
Yeah, it's basically actually milling. We have a powder, and then we use a press. We look here into a method from the Latin Americans, looking into gold in the range of a few ppm. Copper, of course, it's a concentrate of about 20%. Then we have a little bit of lead, zinc, and also silver in the range of 3000 ppm. And the nice thing is here you see the precision is again 0.1% relative for silver, below 1% for gold in the range of below 10 ppm. And yeah, copper is extraordinarily nice, 0.1%, the lead 0.2%. And that's a very nice concentrate, straight out of pressed powder, with a quick measurement time of 6 minutes.
Yeah. So you see, you can with the SA Tiger not only precisely monitor your key major element, which defines also how well your processes are working, etc., but also those which are quite beneficial and might be getting your profit as the side precious metals in your materials. And with this, I would like to switch over again to the lab, to Renata. Renata will now show us a bit more the Tiger in detail, so you get a bit of closer look. She will also talk about our different solutions. And then later on, we see you again for the Q&A, and before that, the summary. Yeah.
Hello, welcome back to our second lab session. Thank you, Adrian, and thank you, Kai, for all the information. Now I would like to show you the SA Tiger, our wavelength-dispersive XRF system. So here in our application lab, we have a configuration with a touchscreen, which is very nice if you just want to start easily measurements and to display results. The system is also available with different kind of loader configuration. So this is something I would like to show you now. The system which we are showing here has a combined loader configuration. So in the front part, you can easily load manually fused beads onto position. And in the back, we have just cups which can be used for different kind of sample shapes or for liquid samples. The measurement chamber is here for all our SA Tiger systems. So the grabber will pick up whether the sample cup will load it into the sample measurement chamber, or the grabber will pick up a sucker, which is here in the back, to handle the fused beads. We also have a different cup size, which is called easy loader cups. So with these cups, you can also easily analyze pressed pellets, you can load fused beads, and for example, polymer samples like this one here. So this is called easy loader cup. And it also comes with this kind of tray, so it's very comfortable if you want to transport your samples. The system can also be connected into an environment of automation systems. So in this case, we have the connection for the automation in the back. So the sample is loaded from the back and is then handled with a grabber. You already heard a lot of information from Kai and Adrian about our solutions called GeoQuant traces and GeoQuant iron ore. So I would like also to introduce you another set of solutions we are offering. So this one is called GeoQuant Basic. So for each solution, you will get such a suitcase with standards and dedicated drift correction samples. Just to show you how this looks like. For this GeoQuant basic set, you will get a set of certified reference material, and of course you will get some dedicated drift correction samples, which are glass samples. Very nice in this set is the samples are already fused and then crushed and grinded, so it's not necessary that you have to mix some fluxes or to add some additives. So you just take the sample as it is, put it into your crucible and run the fusion process. So that's it. This set is available for all our XRF system, and it's covering 40 elements, so it's used to analyze oxides in minerals, ceramics, or geological samples. We also offer another solution, which is called GeoQuant Advanced. So this one is extended up to 21 elements and can also be, of course, used to analyze oxides in minerals, ceramics, or refractories, and also geological samples. And also the concentration ranges are extended, and so you have more type of materials that can be analyzed with this set. That's all from my side today, so I hope you joined the lab sessions, and let's go back to the studio to Frank. Thanks a lot.
Yeah, Renata, thank you very much. And with this, I'd like to conclude the seminar with a short summary. XRF is used along the entire mining process to find and map out new deposits, to monitor and optimize the related processes, and also determine and verify the value of the material. The technique is used to measure the majors, minors, and traces in one method, including the penalty elements, which really influence the cost of the entire beneficiation processes. XRF is used along the entire value chain, starting from exploration, mine planning and operations, to shipping and receiving, to smelting, and then to the final metal production. For each of the required tasks, we are offering an optimal solution, starting with the benchtop EDXRF systems S2 Puma and the wavelength-dispersive system S6 Jaguar. Then to the fluorescent sequential WDXRF system, the S8 Tiger, and then the simultaneous WD, the S8 Lion. Thank you very much for your attention.